Hello, everyone. Today I want to talk to you about the emerging field of data science and my views about its definition and scoping. It is important to have a clear understanding of this field for a number of reasons. First, if you read the literature, it's quite dispersed, and what the field is seems to change depending on whom you talk to. This is not healthy to grow a field. The second reason is that there are data science programs emerging in academia, and many do not have a clear vision of how they see data science. It would be good to have a clear definition of the boundaries of the field. My views are better explained in these two articles. The one on the left is a Communications of ACM article, and it contains much of the technical content of what I'm going to talk about. The second one is a paper I wrote as a Balsillie paper and published by Balsillie School of International Affairs. It goes into a bit more policy issues and positions data science for policymakers. And if you want to dig deeper, then I suggest reading my longer manuscript that I'm still working on. This might eventually become a book. I put the draft as of the beginning of 2024 on archive, and you're welcome to download and read. The recognition of data as an important asset, perhaps the most important asset of an organization, is prevalent. The recognition became widespread over time and started to what is called the big data revolution, which then initiated data science being recognized as among the most important IT developments of recent years. I'm sure you've read somewhere these quotes that I show, or similar ones. The media is also saturated with stories about news related to data science and big data. And as I noted earlier, the terms are used interchangeably, and I'll try to clarify them in this talk. To do an analysis of how the field is growing or how the interest in the field has grown, I did a Google Trends analysis until January of 2023. As you can see, there's a lot of mention of data science and its related terms. Data science indeed very much in discussion these days. Let's take a quick look at the timeline of data science and what the history is. It goes back to 1962 when a statistician named Tukey first made the argument that data analytics should be separated from classical statistics. Classical statistics, he said, is all about mathematics and analytics is different. That's probably the earliest mention of this term. In 1974, Peter Nahr, who was a computer scientist, publishes a book in which he repeatedly uses the same term. In 1977, Tukey writes a second paper where he expands on his ideas, in particular on explorative data science. He's known as the father of explorative data analysis. In 1989, the first workshop on knowledge discovery in databases is organized. This is the beginning of the field that we now know as data mining. In 2001, New York Times published a piece with the title, "All Science is Computer Science," where the author argued that a lot of the things that required wet labs in natural sciences cannot be done in a computer. And this is referred to as the third paradigm or computational paradigm of science. 2002 sees the first data science journal. Not many people know this, but this journal is still around, so that's a milestone. In 2006, Google introduced the Hadoop system for big data processing, which is quite different than database systems. And this is at the height of the big data age. Then in 2009, people started talking about fourth dimension or fourth paradigm of data science, which is really using data-intensive methods. This is the beginning of the modern data science period, in my view. My agenda for this talk is to cover 4 topics. I'll start by discussing how I understand data science and give a working definition. I'll spend most of my time on the data science ecosystem. What are the building blocks of this field? And how should we think about the entire scope of the field? Then I'll turn my attention to data science lifecycle. What is the workflow that's typically followed in deploying data science applications? Finally, I'll discuss the interdisciplinarity of data science and how multiple disciplines impact the field. Let's start by discussing what data science is. The problem with data science is the lack of a universally recognized definition, which leads to confusion. This word cloud that was generated a few years ago from publications on the subject highlights the confusion. Many terms are used interchangeably, and they should not be. Therefore, the field needs positioning. And what I want to do first is to look at some existing definitions to see if we can detect a pattern. When one looks at various definitions of data science, both in academia and in industry, one sees a lot of different definitions, and they seem to differ quite a bit. But when you dig into it, you notice that they have commonalities. They talk about being data-driven. That term appears quite often. Data-driven analysis is used to reveal patterns in data, which lead to insights from data. The definition also refers to the fact that this is a process involving a number of steps that need to be followed. This is my working definition that highlights a number of key concepts. It's a problem solving based on data. I'll come back to this in the next slide, so let me leave it for now. The definition highlights that we're talking about large volumes of data that is potentially multimodal. These are characteristics of what are called big data. Multimodal data refers to the fact that what we are dealing with are not only structured data captured in, for example, tables, but data in the form of text, images, video, social network data, etc. And these come from many sources. The second part of the definition is the process view and states that it involves the steps of collecting, preparing, managing, analyzing, and explaining the data and analysis results. So these are the steps that we need to execute to accomplish what is stated in the first part of the definition. These two parts complement each other, and they should be seen as parts of the same definition. Let me first tackle this issue of data-driven that is very common in literature. I don't like that word, and I don't use it because I'm not sure what it means. It almost implies that the automated decision making without any human in the loop, and that's problematic. I'm fine with using evidence-based, data-based, which is the term I use, or data-enhanced, or even data-informed. They are fine, but not data-driven. And I think in a lot of the literature, there is this terminology of data-driven AI, and you might replace AI with data science, and that would still apply. So why don't I like these automated decision-making systems that are implied by data-driven, and why don't I use data-driven? There are a number of examples. Google Flu Trends is one that comes to mind immediately. In a 2008 Nature paper, they reported that they were tracking people's search activity and they claimed that they could detect flu epidemic 2 weeks before the US CDC. But then it missed the 2013 flu season by 140%, the result of overfitting and not adjusting to changing search patterns. ML-based, machine learning-based tools are used by many companies for hiring, and these are automated tools, but these are known to be hostage to the data on which they are trained, and that data is highly biased, causing these automated tools to work against underrepresented groups. Even during COVID, there were initially very good signs that some of these tools could be useful. Boston Children's Hospital used Health Map system, which scraped online news and social media for early signals of diseases, along with the Canadian health news scraper Blue Dot, which picked up warning signs earlier. And Blue Dot's algorithm even predicted cities most at risk if infected people were to travel. These were all days before WHO and weeks before the rest of the world caught up. But then they actually started failing, that they could not sustain it over long periods of time, and initial enthusiasm waned. And finally, let me talk about this Compass system that is an automated tool that assigns scores to people in the judicial system in US, and that is used for basically assigning what the outcomes are going to be. And these are highly biased against people of color. So I don't like this data-driven, which implies automated decision-making. And these actually all point to big data hubris, but we have bad data sets, automated discrimination, human failures, and a complex global context that is not taken into account. So I always like to have argue that there should be an expert in the system, in the loop, and these systems should not make automatic decisions, but should actually provide input to these experts, or be assisting the experts. So let me start also by immediately addressing two myths that are prevalent around data science. The first is that data science is the same as big data. The terms are used interchangeably in literature. While this is true in popular culture and in the news articles, they're not really the same thing. And as scientists, we need to be more careful. Someone likened big data to raw material. You have the raw potential, and you have the raw material with a lot of potential, but now you have to do something with it. And doing something with it, or in other words, processing it, is what allows you to leverage this resource. It gives you a better understanding, and that is what data science is. In data science, applications are supreme. If you really don't have applications, you don't have data science. You basically have a big data processing. And I'll come back to this point. The second myth is that data science is really machine learning, or it's a subset of machine learning, which is a subset of AI. Or some claim it's the modern AI is all about machine learning, but that's besides the point. This is also wrong. The data science and AI certainly overlap in the use of machine learning and data mining as part of the data analysis process, but they're not the same thing. Data science and AI have their own domains, and they're larger than each other. AI has a number of other concerns, so does data science. And in this talk, I'll try to convince you of the additional issues that data science has to deal with. I made the comment earlier that data science is all about applications, or applications are dominant. So let me focus on that aspect a little bit. The question is typically asked, what is a good data science application, or what is a good candidate for a data science application? The proper answer is probably that almost any application that either generates or consumes large volumes of data from multiple sources is a good candidate. I give some examples here, but I won't go into them in detail. That requires a separate talk. But applications give purpose to data science deployments, and they inform the core technologies of what are useful and what are not useful. Let me talk about data science ecosystem. This focuses on building blocks of a data science deployment. Data science builds on a core set of technologies in data engineering, data analytics, data protection, as well as data ethics. And these are in close interaction with application domains, as I mentioned, and the application domains leverage these technologies to solve their most important problems. Because applications are so important, they surround the core and inform it. The technologies, methods, tools, and approaches developed within the core also assist the applications. Similarly, data science deployments are never done in a vacuum, and there is always a social and policy context. That context also envelopes the core. This figure is probably the most important take-home message I have today, namely that data science is interdisciplinary, broad, and has a number of non-STEM components. In the next few slides, I want to dig into each of these data science pillars. My objective is not to fully survey each of these areas, but to highlight the significant issues as they relate to data science, given the definition that I've used. The first building block of data science ecosystem is data engineering, and it focuses on managing the big data sets that are used in data science deployments and getting those data sets ready for analysis. Data engineering consists of two components. One is the big data management. Big data doesn't have a good definition, but we know the 4 V's: volume, variety, veracity, and velocity. The concern is to manage this data. Data comes from multiple sources, so we need to do data integration, either as a data warehouse or a data lake. We need to worry about storage and management of these big data sets and the platforms for their processing, efficient processing. The second part of data engineering is data preparation, which is the process of taking the data and making it ready for analytics. It involves both acquisition and gathering of data and its cleaning. For data veracity, the provenance and lineage of the data needs to be captured and managed. It is important for me to note that although these are discussed as two components, they are not independent of each other. They interact, but thinking about the data engineering scoping as these two components makes it easier to discuss issues. Let me talk about data integration and the classical way of data integration is with a data warehouse. We're taking data from multiple data sources, and we don't really need to take the entire data in these data sources, but we some of the data from these data sources, and then we load them into a data warehouse. And the data warehouse has a schema of its own. So the data that we put into the data warehouse has to match that schema. So we use this extract, transform, and load process. And sometimes the order is reverse: extract, load, and then transform. But let's use the classical one, which is extract, transform, and load. We're extracting data from big data sources, transforming that data to match the schema of the data warehouse and then loading it into the data warehouse. That's the process. Since the data has to match the schema of the data warehouse when we're loading it into the data warehouse, these are typically called schema on write. So we enforce the schema during the write process. That's important. There is a process where we usually keep transactional data from these big data sources in an operational data store as they're processed, and because this data is also subject to transactional processing. And the data from these operational data store are periodically moved into the data warehouse as historical data, and that enables the data warehouse to keep temporal data, and historical data for analysis, for example, for trend analysis over time. And then when you run your task on the data warehouse and get the results, you're many times obtaining aggregates, and these can be done as downstream tasks. And frequently, these results of these analysis can also be pushed back into the operational data store for later use, but that's not shown in this figure. So this is data warehouse. The more the contrast to the more recent approach in data integration is data lakes. In this case, we still take data from big data sources, but we just dump them into this storage called data lakes. And the data lake does not have a schema that is enforced. The data goes in there in its raw format. The schema is dependent on the downstream tasks. Each task wants to see the data in a particular format. So then when the data is pulled out of the data lake, then it's converted into the format that the downstream task wants to see. So in that sense, these are called schema on read systems, where we're enforcing a particular schema when we're reading from the data lake. In another sense, you might actually think that the ETL in ELT is moved from the input to the output. That's another way to do it, to think about it. The data lakes are easier to participate because you just dump data in its raw format, but they're harder to use because now you have to do a lot of processing and searching in the data lake for appropriate data and then processing to match the needs of the downstream tasks. The second most important aspect of data engineering for data science is data preparation. This is the process from acquiring the data all the way to getting it ready for analysis. It typically involves 4 steps: data acquisition, selecting the appropriate data sets for the question at hand, integrating those data sets into an integrated data store of the type I discussed, and then analyzing and doing data cleaning and getting it ready for data analysis. Sometimes the data integration and data set selection steps are reversed. In this case, you'd integrate the data first and then find the data sets in that integrated data. This is probably a more appropriate way to do data preparation in the data lake environment, where you put the data in raw format and worry about how you use it afterwards. The data quality is considered mission critical and a success factor in how you do data preparation. It tops the list of challenges for data integration, primarily both in data warehouses, but more so in data lakes. It constitutes a major portion of the data preparation effort for most organizations. because of its importance. And this is a problem area that we keep working on. So it's real. The You might actually wonder why I spend so much time and put so much emphasis on data engineering. And the reason this data engineering essential and you worry about it so much is that if you do not manage your data and get it properly prepared, it won't matter how good your analysis model is. What you will get out of that analysis will be junk. The old saying of garbage in, garbage out most certainly applies in data science applications. And data engineering ensures that you are not putting garbage into this analysis phase. The next pillar of data science, or the next foundational building block, is data analytics. This is where most of the attention is paid, and most people consider this to be equivalent to data science, but I hope I'm giving you a broader picture. Data analytics is defined as the use of statistical and machine learning techniques to understand the data and the system under study. This is a broader definition than what has been traditionally used. Tukey, as I said, is the father of exploratory data analysis, defined data analytics as, quoting, procedures for analyzing data, techniques for interpreting the results of such procedures, ways of planning the gathering of data to make its analysis easier, more precise or more accurate, and the machinery and results of mathematical statistics which apply to analyzing data. This is a definition in 1961. I think part of Tukey's definition is so broad to encompass most of what we call data science today, and that also has led to a confusion about whether data analytics is really all there is to it in terms of data science. The data analytics involves both statistics and computer science, particularly in data mining and machine learning. The distinction about the contributions of each of these disciplines is a constant topic of discussion. I'll say more about that towards the end of the talk. For the time being, perhaps the distinction made in this paper by two biologists and one statistician is a good starting point to discuss the complementary contributions of each of them. So they actually say that statistical methods focus on inference, which is achieved through the creation and fitting of a project-specific probability model, and machine learning concentrates on prediction and using learning algorithms to find patterns and enrich and unwieldy data. And they basically say machine learning works well when the number of variables and the associations between them are large, so building a model is not easy or feasible. The lines between these two disciplines have been blurred, and that's just fine. I don't think that is an issue at all. One aspect of data analytics that's important to consider for data science is the alternative types of data analytics. Usually four different types are identified. Descriptive, the question is that descriptive analytics tries to answer is what happened or what does the data tell us? It's retrospective and quite popular. It's retrospective in the sense that it looks data from the past. One particular version of this is exploratory analysis, where what we're looking for is discovery. Either the data reveals what we know, so that's confirmation, or it reveals something new, which is discovery. Exploratory analysis typically depends on visualizations and visual analytics. The second type is diagnostic, which is also retrospective, but now the focus is figuring out why the data reveals what it reveals. This may require data mining techniques to discover things from the data. The third is predictive, and this is not retrospective but forward-looking. It provides calculated predictions of what is likely to happen. And it uses machine learning, data mining, and predictive modeling techniques. Finally, there is prescriptive, takes the information that's been predicted and prescribes calculated next steps to take. And it typically requires heavy machine learning usage to monitor and identify new rules. Predictive and prescriptive together are sometimes referred to as advanced analytics. On the right, I'm showing you how these stack up along two dimensions, complexity and value. As you can see, going from descriptive to prescriptive, things get much more complex, but the value that you get out of these models also increases. The other aspect of data analytics that's important to consider for data science is what kind of tasks we're using, and choosing the right task for the question that we're targeting is important for success. Usually 4 different types are identified. Clustering is finding meaningful groups or collections. Some example applications are market segmentation, social network analysis, grouping of search results, and medical imaging. Second is prediction, which predicts the future value of a variable or variables. In the case of a regression model, we're trying to find a model that best fits the data and develop that model. And the model links a dependent variable or a set of dependent variable to one or more independent variables. And that's how you predict the value of the dependent variable. In the case of classification, the value of a variable is predicted to fall into one of a set of predefined classes, and that's the task. The third is association rule mining, which is discovering interesting relations between variables in large data sets. Market basket analysis is the best known example and the classical example that's given for association rule mining. Finally, outlier detection, which is also called anomaly detection, and it refers to identification of rare items, rare events or observations, which differ significantly from the majority of the data. And the typical applications are fraud detection, medical problems, errors in text, etc. The third major element of data science ecosystem is data protection, and involving security and privacy. In a sense, there isn't much that needs to be said on this topic, since the core of data science is data, and the volume of data and the multiplicity of sources from which data are collected make the importance of the topic quite obvious, or increases its importance. However, I'm going to take a look at how data security and privacy concerns exhibit themselves in data science. Well, let's start with the threats that exist in the big data environment. 4 different categories can be identified. Data breaches. Almost all of us have been subject to more than one data breach. It's almost always more than one. Surveillance, nation-state actors and companies aim to collect every piece of data for surveillance or economic purposes. Mis and disinformation, which are attempts to provide false information, and these have become quite popular and regular recently. And finally, infrastructure attacks. The big data environment is diverse, and the infrastructure is complex, and the entire infrastructure is under threat and needs to be protected. The dimensions of data protection are twofold typically. The one aspect is data privacy, the complementary aspect is security. And data privacy is concerned with proper handling, processing, storage, and usage of information. It's really all about the rights of individuals with respect to their personal information. The data security is focused on protecting personal data from any unauthorized third-party access or malicious attacks and exploitation of the data. And these two aspects are complementary to each other. Let me end this part by referring you to a set of recommendations from the Cloud Secure Alliance. They have a set of recommendations on what should be protected and how, and these fall into four major categories: infrastructure security, data privacy issues, data management and integrity, and reactive security, and which is going back and looking at it after the fact. And in this space of data protection and data science, all four of these categories need to be addressed. The fourth and final pillar of data science is data ethics. What data ethics refers to needs to be clarified. Most certainly it has a significant relationship to data privacy, but how should we think about it more broadly? I give a definition here, which is from a philosophical perspective, but it's important in that it recognizes the ethics issues related to three dimensions: data, algorithms, and practices. And these three form the axis of a design space where each point identifies a particular ethical problem. Ethics of data are ethical problems posed by the collection and analysis of large data sets and on issues ranging from the use of big data in diverse set of applications. Ethics of algorithms address the issues posed by increasing complexity and autonomy of the algorithms. Finally, ethics of practices addresses the questions concerning the responsibility and liabilities of people and organizations in charge of data processes, strategies, and policies. And you can think of example data points along these three dimensions quite easily. One topic that is that falls under ethics that has been extensively studied and has been a topic of quite a bit of interest is bias. So I'm going to spend a little bit of time talking about that. Human biases get reflected in data science in two ways. One is in bias in data. In machine learning deployments, this is the bias in training data. And bias can be introduced through historical data. If you look at, for example, the arrest records, for example, in the US, more arrests are among marginalized communities, primarily because they are over-policed. So historically, more of them show up on the data that might get into your training data. Bias might also be introduced due to underrepresentation. In known case is face recognition systems that are known to perform much better on white male faces than others, simply because 80% of the faces collected in data are from whites and 3/4 of those are male. The second is in bias in model or algorithms. In machine learning deployments, this is the feature engineering that people talk about, and deciding to include which features in your model is one aspect of it. And the inclusion or omission of features will introduce bias. Certain individual attributes are commonly labeled as protected attributes, and because they can be sources of social bias. These are typically race, religion, national origin, gender, marital status, age, and socioeconomic status. When you omit, for example, gender from your set of features, you cannot just claim that your algorithm is gender agnostic or omit race and your algorithm is not racist. I mean, in some countries, the postal codes are correlated with race. And we have to be careful here. Statisticians typically use the term algorithm to mean model. And in that setting, the algorithmic bias includes bias in both data and algorithm construction. Here I'm using the term algorithmic bias more narrowly to refer to bias in model algorithm construction. There are examples. I gave the compass example before. There are examples of the algorithmic bias in how healthcare is allocated based on race because the algorithms are biased. A category of this algorithm and bias is this unmeasurable outcome. Sometimes what you're trying to analyze is not measurable, and then you use proxies for it. A typical example is in academia when we're doing admission decisions for grad school, for example, we're trying to decide whether a candidate is going to be successful in the grad program. We have no good metrics for doing it, so we use proxies such as GRE exams, which have been shown to be quite biased, and they introduce bias. So that's another issue. It is really not that clear cut. The boundary between data bias and algorithmic bias can be fuzzy. And typically you will hear that the phrase data does not lie, which may be true, but the data may be wrongly interpreted. So we need to be careful and with about and cognizant of the potential biases. Although bias has been the main focus of much discussion, I suggest that we should think about data ethics broader than bias. The data ethics includes questions of ownership, for example, who owns the data? And this again changes based on jurisdiction. It includes transparency concerns, which is that the subject of the study should know data about themselves that you're collecting, and how you're going to be storing and processing that data. And user content in this context is of paramount importance. Privacy concerns are part of ethics, and this is the overlap with the data protection that I mentioned earlier. The personally identifiable information and how it should be treated. These are ethical considerations. And finally, intentions. What are you planning to do with the data? In particular, secondary use, which is really what I refer to as third-party use under data privacy. So if you're going to share this data, what are those third parties allowed to do with this data? Big Data Group at Berkeley has come up with a checklist that you should be using to ensure that you have reasonable coverage of ethics issues. These are formulated as a set of questions that those of us who work on data science projects should be asking ourselves. On the right side of the slide, they list the concerns that each question is addressing. I won't go through this in detail, but they're reasonable questions that we should be asking. I want to end this section by recalling that the data science ecosystem, particularly the importance of the social and policy context. A number of issues I discussed, in particular data privacy and ethics concerns, are related to social and policy context. There are many things that you need to consider depending on the context. The interaction between public policy and societal concerns and data science are bidirectional. The public policy and social context certainly inform and influence data science. This comes in the form of legal and regulatory frameworks. These could be general, like GDPR, or CCPA and other data protection regulations that influence data collection and processing. They could be topic specific, for example, regulations governing monopolies and anti-competitive behavior in data-driven markets. Or they could be sectoral, for example, industry-specific regulations, such as those in the healthcare sector and healthcare privacy rules and financial data sector are important. And finally, the societal customs and conventions play a significant role. Societal expectations influence what data is considered acceptable for collection and what is acceptable for processing. And certain data may be restricted or unrepresentative due to cultural influences. So data on the other direction, one hopes that data science influences public policy and social activities. Data science plays a vital role in public policy by providing a robust and evidence-based insights for informed decision making. And if you're using advanced analytics and predictive modeling, policymakers can better understand societal trends, anticipate future challenges, and devise effective interventions. Data science facilitates the evaluation of policy outcomes and impacts. It enables governments to ensure effectiveness of policies, identifies areas for improvement, and continually adapt strategies. Data science also enables optimization of resource allocation in public policy. You can use data-driven assessments to decide how funds can be allocated more efficiently and identify areas with the greatest need. After this discussion of the data science ecosystem, let me talk about the data science lifecycle. There is this notion of data lifecycle that tracks what happens to data from its creation to its demise, so to speak. And there are variations of these steps, but what I'm showing here is probably the right framework to talk about the data cycle, and this is quite common. There are variations of this that have appeared in other publications as well. And the problem I have with this view is that it gives the notion that the process is entirely linear. You start somewhere, you follow a number of steps, and you get to a particular point, and you're done. And this is not the right way to think of it, in my view. So how should we think about this? We start by recognizing that the life cycle is not linear. It's repetitive, and it's a living process where certain steps need to be revisited through feedback loops. Therefore, I look at this as a cyclical life cycle. It has a number of processing steps, and each of these processing steps have a number of questions that they address. And we start with a research question, then we prepare the data, then we worry about how we store and access the data, then we analyze the data, and then we deploy the data science system and monitor it. If necessary, we go back and revise our research questions and repeat this process. At the center of this is data, of course, and this lifecycle definition incorporates sufficient feedback loops from data analysis to data preparation. It might mean that I don't have the right data, so I need to do data preparation again, or I don't have clean data, so I have to repeat that process, or the problem is underspecified, so I have to go back to the research question and consider again. Surrounding all of this is data protection, data ethics, and societal policy issues. And they're shown as surrounding all of these steps because they cut through all of these steps. They have an influence on every one of these processing steps. So this is the way that I think about this. So if you believe in dialectics, the process is one of dialectics. So every time you come back to the research question, you're not back to square one, but you're basically at a higher level of understanding. So it's a helical dialectic process. What I've discussed so far are the four pillars and problems in those four pillars. And I argued why they should be four pillars. And then I gave you a life cycle, which also includes a number of processing steps. So whenever one creates these types of figures and organizes the discussion along those steps, it creates the appearance that these are isolated silos, both in terms of the pillars and in terms of the processing steps. In fact, the activities in each step influence each other and contribute to the broader goals of data science project. And it's really important to emphasize that most interesting research issues arise at the intersections of these steps or pillars. And these are usually the harder problems, but also the more interesting, and that they should not be ignored. All of these fit together as multiple gears to make the entire system work. Let me finally touch upon the interdisciplinarity of data science. You may or may not be surprised to learn that there is a tug of war as to who owns data science. This was really an active discussion topic. It's thankfully dying out a little bit, but almost every field, every discipline claims to be doing data science and owning data science. And there is, in particular, between computer scientists and statisticians, there is this traditional tug of war, and the argument that CS types make are typically that statisticians know how to deal with small data, while data science is all about big data, for which machine learning, etc., are more appropriate. And statisticians have long felt wronged by the growth of independent data science programs, and they've claimed that they have been doing data science for decades. I quote two pieces from statisticians that highlight their frustration, and some of it is well-founded. This discussion requires identification of the type of people and communities that engage in data science. So there are really, in my view, this is an oversimplification, but there are three stakeholders. One category are core technology people. These are typically STEM people who work in the core and develop technologies, tools, and methodologies. And they engage in data engineering, people who work in machine learning, algorithm development, or applications, and people who work in privacy and security technologies, privacy enhancing technologies, and so on, and statisticians who work on modeling and data analysis, mathematical optimization, people who work on algorithm optimization, etc. These are in the core technology people. The second category are people in various fields who work on interesting data science applications and depend on the tools and techniques developed by the first group. And these are, for example, biologists, physicists, health professionals, environmentalists, you name it. These are people who own the data science problem and who work with large data sets. And they're really focused on developing application technology, not on the core technology, but they want to use the core technology. The third group are people in social sciences and humanities that may own applications, for example, digital humanities. So they would, in that case, fall into the second group of stakeholders. But in the third category, they focus on ethics, societal impact, policy, and legal issues. And the data science ecosystem would involve all of these people, which actually makes it harder to define the field and the scope of the field, but it also adds to the richness of the field, and it should be considered. All of these stakeholders should be considered in the conversation. This who owns data science has bled into discussions of positioning data science, and typically Venn diagrams have been used. They're very popular. So one very well-known one that is really espoused by statisticians is this Conway diagram, and this was a diagram drawn by Drew Conway, who and he and if you do a web search, you'll find his blog. If you really look at this, there's no role here for computer scientists. In fact, and I'm quoting, he says, "This does not require a background in computer science. In fact, many of the most impressive hackers I have met never took a single CS course. Being able to manipulate text files at the command line, understand vectorized operations, thinking algorithmically, these are the hacking skills that make for a successful data hacker." And so that's basically his view. It's all about math and statistics, substantive expertise, which is domain expertise, and hacking skills, which do not include computer science. And that's and he calls it particularly a danger zone, but unfortunately, it's that danger zone where a lot of interesting work is done. Computer scientists' view, as you can imagine, is that computer science has a much bigger role. This recent diagram by Jeff Ullman, and the diagram claims that machine learning is uh, is really within computer science, which is correct, and the intersection of machine learning and the domain science, which is again domain expertise, is where the data science is, and the role of math and stats are really peripheral in his view. Um, there is a less known but more balanced diagram by Vogt, which I like better, and this is more balanced, and it says that the interdisciplinarity of data science is balanced between computer science and math and statistics, plus the domain knowledge and the domain expertise, and this is more common. But I'm really not convinced that these really capture the essence of interdisciplinarity of data science. The discussion is heavily STEM oriented, and it is really not helpful. It doesn't contribute to defining the boundaries properly. If we're going to use a Venn diagram for this, I prefer a much broader one. I prefer this one, which identify captures all the stakeholders here that we talk about. The data science binds together the many STEM fields, ranging from computer science to mathematics to statistics, as well as non-STEM fields, low social sciences and humanities, and as well as application domain expertise. So if you look outside in, this is basically data science bringing in aspects of each of these disciplines into this field as defined in this talk that I tried to convince you of. If you think about it inside out, then it's basically data science going into each of these fields for its techniques and applications. So I thank you for listening.